Welcome back as we continue with the second part of Chapter 2, Linear Momentum. Okay, if you just observe the motion of a ball shooting a basketball towards the rim, what are the things that we can study and how can we use linear momentum in order to study the motion of a ball? Newton's second law and linear momentum. Before we start with this part, okay, we go back to grade 11 or previous classes when we studied that Newton's second law is the following. Summation of F external equals to MA. Now we know that A is dV by dt. So how are these two ideas linked together? How is Newton's second law linked to linear momentum? Let's see. The time change of linear momentum of a system is the net external force acting on the system. dP by dt as a vector equals F net as a vector, which is summation of F external. In most scenarios, mass is going to be constant. Keep that in mind. So if we just apply the rules that we know, whether for linear momentum or for the acceleration things or kinematics, summation of F external equals dP by dt. Now P being mv, so we replace P by mv, so we have dmv by dt. Mass is constant, so it exits the derivative. M dv by dt is nothing but the acceleration, and voila, here's the equation. Summation of F external equals dP by dt equals to ma. From now on, we're going to use Newton's second law in this format. We're going to insert dP by dt in between summation of F and ma, which we used to know from before. Now, if we focus on problem solving, whenever we need to use Newton's second law in an exercise, directly we use it in one of these 5 forms that you can see over here. Summation of F equals dP by dt. dP by dt can be replaced by dmv by dt or m dv by dt, where m is constant, or simply ma. Now these 5 terms are all the stages of Newton's second law. However, the most important are this step, and the final step. Now, with time, you will know which of these forms to use more and more. Another idea is treating dP by dt. Now, dP by dt is nothing but the time derivative of momentum. Okay? If you're given the function of momentum, you can simply derive it with respect to time. If not, and you need to calculate or measure, dP by dt can be replaced by delta P by delta t. Here, emphasis on the difference in notation. Delta P by delta t, which is the variation on a large scale, which equals dP by dt, which is the variation on a small scale. These two are equal and they are equivalent. We can replace dP by dt by delta P by delta t in 3 different scenarios. Keep them in mind. First, when delta t tends to 0. So when delta t tends to 0, this is the definition of dt, then we can replace delta P by delta t by dP by dt. Or in fact, we can replace d by dt, which is the derivative, by delta P by delta t. If delta P by delta t or the external forces acting on the object are constant, or the sum of F external is constant, in these 2 cases, we can also replace dP by dt by delta P by delta t. Third, and which is also very important, is that when the variation of momentum, P, with respect to time is linear. In this scenario, you know the slope, which is rise over run, is delta P by delta t, which is change in y over change in x, which is also equal to F external. So you notice that these 3 terms are somehow related, but I like to state them here like 3 different scenarios so that if you're solving an exercise and you need to evaluate dP by dt and you don't have any derivative applications, you can replace it by delta P by delta t if any of these 3 cases is or are met. Okay? Now, let's go check an exercise, an application, and try to benefit of this note or these notes that we have mentioned here in that application. A box of mass 0.8 kilograms is left to slide down a ramp inclined by 30 degrees with the horizontal. The document aside shows the variation of a cylinder momentum relative to time. Take G equals 10 newtons per kilogram, and let's answer the questions. Determine graphically the magnitude of the net force acting on the box. Prove that friction is not neglected, and then calculate its magnitude. The first question is to determine the net force acting on a system, and what we're given is a graph showing the variation of momentum P as a function of time T. So I shift my attention to a link between momentum, time, and force. The only thing that comes to my mind is that F external is the variation of momentum with respect to time. Now this is known as Newton's second law. So here we go. By Newton's second law, dp by dt is summation of F external as a vector relation. Now, the graph shows the variation of momentum as a magnitude with respect to time. So in magnitude, the net force is nothing but dp by dt till here. Now, since the variation is linear, if you remember the graph is a linear function or a straight lines have constant slope. dp by dt is the derivative of that line or the slope of that line. In other words, you can simply replace it by delta p by delta t, since we have a linear variation. Thus, F net equals slope. Slope is rise over run, rise over the run. We take, let's say, this point and this point. 12 minus 0 over 4 minus 0 equals 3 newtons. So the net force acting on that object, which is given to be sliding on a certain ramp, okay, sliding, the net force is 3 newtons. The second question is to verify that friction exists. Okay? In order to link that, friction is a force. So I will try now to move to forces. Okay? We won't use any more momentum. We'll just focus on forces. In order to do that, a very good start is to draw a figure showing the forces. I already started here. If I change color, forces acting on the object, basically we have the weight, trying to pull it down, and definitely we have the normal reaction. These two forces are trivial. Weight, since the object has mass. Normal, since the object is placed on a solid surface. Now, one more force, which is not known yet, is friction. Do we have friction, or should it be neglected? A question that we should ask, right? However, since the question demands us or asks us to determine friction, we suggest that friction exists. Okay? So, external forces acting are weight and normal reaction. Summation of F equals weight plus normal. In the approach that we can read here, we neglect friction, or in fact, I won't use the term neglect. We ignore and forget about friction now, supposing that there is no friction. Along the x-axis, motion is on the plane, okay? Summation of Fx. So here it's important to draw a figure showing the x-axis, okay? Here is the box, okay? Forces acting, as we said, are weight and the normal reaction. Projecting them on x-axis, okay? Summation of Fx equals weight x, normal x is 0, so it left with mg sine alpha. You remember the projection from previous classes? If this were alpha, so this is alpha, so we get mg sine alpha. Now, summation of F equals 4 Newton simply by replacing m by 0.8, 10 sine 30, 4 Newton. That's weird, huh? The summation of net forces on x is 4 newtons, while the previous calculations produced 3 newtons. Now, having Fx more than 3 newtons alone makes us think about a force which will try to reduce this value. Someone might ask, what about Fy? You are right. If Fy exists, okay, if it does, then the net force or the sum of forces on x and y will be even more than 4 newtons. The net force is 3 newtons. So there is something here missing. Okay? So 4 newtons is greater than 3 newtons. Therefore, there should be one more force which acts against sliding. This force is nothing but friction, and its magnitude is 4 minus 3. Now I can add here no motion on y, okay, to consider. Summarizing everything we have seen so far. So, to apply Newton's second law in linear momentum form, the equation is summation of F external equals dp by dt, and that gives ma as well. Okay? Just focus on the projection techniques, whether you want to use vectors or xy projections, it's all up to the exercise. Now, to make sure that all ideas are grasped well, let's solve this homework, solve this exercise, and as we always do at the end of the lesson, we're gonna post a video explaining all the exercises of all the chapter. In this exercise, we have a skier moving from A to B on a horizontal road. The skier is being towed or pulled by a rope. That rope exerts a constant force F. There are some frictional forces. The first question is to apply Newton's second law on the skier to express the acceleration of his motion or their motion. Then determine the expression of the velocity and use it to determine speed. To determine F. That's it concerning this exercise. Try to solve it, okay? In the upcoming session, we're gonna talk more about Newton's second law. We're gonna focus on the projectile motion and some mathematical complexities when we deal with that, okay? So this simple equation of sum of F equals dp by dt might be challenging in a certain situation. We'll see that in the upcoming session. That's it so far, okay? Just review these, try to solve the exercise before you move to the upcoming session, which is another application about Newton's second law using linear momentum. Okay, thank you for your time and see you next time.